Today I am going to try a different strategy, which is to use slides. The main reason is because I am going to be dealing with programs, and it takes a lot of time to write programs. So it's easier if the programs are there on the slides. Okay. So in the first two lectures, what we have seen so far in the first lecture we looked at contention, okay, and then basically in the second lecture we again looked at resource sharing, which is a similar problem, and so we looked at various kinds of distributed algorithms and saw that implementing them takes some difficulty, and we actually move into a real programming language and try to see what happens at that end. Okay, so let's see. So this examples which I have taken are from this book. It's by Gregory Andrews. It's called Foundations of Multi-Threaded Parallel and Distributed Programming. But there are many books. I mean, I'm not saying this is the only book you can look at. So I'll begin with threads. So I'm going to essentially use Java. I mean, I'm not really talking about too many programming languages. I'll stick to Java. So I expect, I mean, you know this, but if you don't know, it's just I mean, if you know this, it'll be kind of boring because it'll be just a reminder of what you know. If you don't know, then you get some idea of how this is done in Java. So Java, as I'm sure you know, is based on classes. I mean, everything is defined in terms of classes, and there is one class called object, okay, which is the kind of base class, and every class then extends this. There will be a class extending this, and then there will be classes extending this, there will be classes extending this, and so on. That's how the Java class hierarchy is built up. Okay, so you're absolutely sure that any class at all extends thread always. Okay. So in Java, the way you define concurrent threads is you define a class which extends a built-in class called thread. Okay. So if you have such a class, so I've created such a class. Okay. So this is all just Java jargon. You call it a public class, means it's to be visible outside. Okay. So the class's name is window. Let me use enter. Yeah. So the class name is window, and it extends thread. It contains an integer which we use to record the ID. Okay, and how is it created? This is the constructor method for the class. So you give it the integer, and that is what it sets its ID field to. Right. So inside this class window, so here is window, and inside this window there is one thing called ID. Okay, and initially when you create this class, you have to pass it that ID, right? And then there is a method called run. Okay, so what does this method called run? So there are two. This is a constructor. Although it looks like a method, it's actually the constructor because it has the same name as the class name. And there is a method called run. It's void, meaning it has no output, and it takes no arguments at all. And what it does is 100 times basically it prints window and ID, right? And after that, what this thread does is it goes to sleep for 1000 milliseconds. Okay, and in case there is an interrupt, okay, then there is an exception that is caught by this, and then the something called command handler is called to handle this. Okay, so this is the base class. I mean, anything about this which is not clear, I mean, I'm assuming that all of you know some amount of Java, but even if you don't, you can ask me, there is no problem. Yeah. So this is how you have, so now this, so there is a run method which does all these kind of things, okay, right. So this is the Windows class, and now to run the Windows class, we actually we write another class which is called TestWindows. Okay, so this is what it does. Yeah. So what TestWindows does is, it has a method called main. Okay, and it doesn't return any argument, and it's declared public and it's declared static. Okay, and as an input it takes a string. Okay, so this is a string, meaning it's a character array, and it's called arguments. And what you have is, what this does is it allocates space for this array W, which is basically 5 windows. Okay, so you create an array of windows and you say how many of them you want. So you get 5 for this. And what does this loop do? This loop basically creates a new window with I as parameter. So it creates window with an ID 1, window with ID 2, window with ID 3, or whatever, 0, 1, 2, 3, 4 windows with those. Okay, and then it you call wi.start. Okay, what this does is, the method which is called run in wi is started off by this. Okay. So in Java, okay, so this one has a method called run. It has a field called ID and a method called run. Okay, and when you create a window of this kind, so you first create, so in this case we created 5 windows of this kind. Okay, and so you created some array W, and now when you say wi.start, at that point this method is executed. Okay, so this is, so you might wonder, this is a bit strange. I mean, why not call it wi.run? Okay, we'll just commit to that in a minute. Okay, so this is how you create threads in Java and start them off. Okay. Yeah. So here it is. If we write wi.run instead of wi.start, then wi.run will run. Okay, and when the control is over, when that run method finishes, it passes back the control to the caller, right? Which means that after this thing will come back to this TestWindows class, and inside the TestWindows class, then you can do something else. Right? But here we are not actually interested in getting back the control, we just start it off. So wi.start, what it does is, it starts off the run method, and when that run method is over, this class is also over. The execution of this class is also over. Okay. Right. So this is just quite a straightforward thing. Okay. So okay, there is a weakness of this thing, which is that what you did is, so here is a window which extends thread, and thread of course extends object. Okay, and now you started off this, so you have this class called TestWindows, inside which you declared all these windows. Okay, and then you called this. Okay, now inside this particular class, if you want to create more threads, okay, so if you want to have a structure in which there is parallelism inside parallelism, okay, that you cannot do. At least in Java you cannot do it, right? So, so what you do is there is another class provided, an interface class called Runnable. Okay. Okay. And a class that implements Runnable is defined in the same way as one that extends thread. Okay. So it's basically again the same kind of methods you have to provide. You have to define a method called run. Okay. And however, to invoke this in parallel, we have to explicitly create a thread from the runnable object by passing the reference to the object to the thread constructor. Okay, let's see how that is done. So first, this is how you do the runnable class. So you have a class window which implements the interface class called runnable. I mean, this is the only line which is in. After that, everything looks the same. Okay, you have, so window does not, earlier you had said window extends thread. Now you say window implements runnable. Okay, and everything else remains the same. So nothing else changes here. Okay, now here is the class that uses the runnable class. Okay, signed. So now what do you do? So now you have two arrays, an array of windows and an array of threads. Okay, so you create these two arrays. Okay, now what do you do in the loop? You create a window. Okay, then you create a thread, and for this thread, the code that you give is wi. Right. So you give the class wi as an argument to the thread class. Okay, so now that means that you have a thread ti now, which is running the code w. Okay, and so now you do ti.start. Okay, and ti.start will start wi.run inside that thread. Okay. So in this way you can have threads. I mean, so basically there are two ways to create threads. Either you have a thread in which you don't want any sub threads, or you do. If you do want threads inside subthread, there is a slightly longer procedure that you have to go through. That's all. So here is a kind of summary of what I did. Okay. So a Java thread is a lightweight process. Okay. So what does that mean? It has its own stack and execution, its own runtime thing, and it has direct access to all the variables in its scope, right? And to program a thread, you either define a new class that extends thread or implements runnable. Okay, you define a run method in the new class which contains the code of the thread. You create an instance of the new class with using the new, and then you start the thread off using. Okay. So that's the basic way you run threads, and now you can program these threads to do anything. I mean, they can. So the one which we saw, basically, what it does is it prints on the screen something like it will print Windows 0, right? This is what it does. It prints this 100 times. Okay, but there are 5 of these threads. Okay, so there will also be another thread which is printing window 1, and so on. So what you will see on the screen is actually some interleaving of this. Okay, so there will be some zeros, and in between there will be 1s and 4s and 3s, and they'll come in any order. Okay, because all the threads are running concurrently. That depends on. Okay, so if you don't see this within 100, then try printing it the loop some 1000 times or something, and you will see this. Okay, because it basically depends on the speed at which the switching between threads is done by the scheduler in the operating system. Right. So if you do this, you will actually see on the screen these things appearing in different order. So just to illustrate how threads work, just a very straightforward example, and you can run it on any Java compiler, and it should give you this. Yeah.
So use of the try catch statement is there?
Of a?
Catching thread exception and command handler.
That's because no, what we did was we had a sleep. No, now how do I go back in this? Okay. Right. So I put a sleep out here. Okay. So basically, what you do is you print this, then you sleep. Okay. Then you print this, then you sleep. Why do you do that? Because if you just say print, then the thing will go fast on the screen very fast. You won't even see a thing, right? So you won't actually see these things appearing. So I put a sleep for some amount of time, right? So that it prints, then it waits, then it prints, then it so you actually see things appearing on the screen one by one. Okay. So again, basically all these parameters you can change. It will depend on your particular CPU speed and so on. You know, and maybe you might have to sleep for longer, or, right? So, and what this does is this just goes to sleep. Okay, and after 1000 milliseconds, the operating system will wake this thing up, and that at that point this will come out of this, and the exception handler will catch it, right? Okay, right. I don't know what command handler is supposed to be.
Instead of just trying catch,
Yeah.
a loop for which runs for one second.
Sorry.
Can you put a loop which eats up 1 second time?
But how do you know?
Using the sleep command.
Yeah. Yeah, sure. Anything. Yeah. I'm just slowing the printing process down. That's all I'm doing. I'm not doing anything. But the advantage of this is this process goes to sleep, which means that another thread gets a chance to run. If it's depends on how many processors you have and so, right? So that's the advantage. If you put a busy loop, then maybe the process will schedule it in such a way that it keeps on doing it without switching to another process. So that's all. So I'm going to put these slides up, so you don't need to copy things. Okay, so this is the basics that you need to know about threads. Okay, now let's start on doing something with these threads. Okay, so now here is a kind of schematic of a parallel algorithm. Okay. What it does is, so typically what happens is each iteration depends upon the results of the previous iteration. Okay. So you will have something like this. So while not completed, there is some condition which is going on. You create a thread. Okay. So this process is supposed to be a thread. Okay. And so in the loop, what do? You create these threads, and then you start them off. Okay. So the idea here is that you start off these 5 threads in parallel. They all do something, then you come back here. Okay. Then again you do some processing in parallel. You do something, and you keep going like this, right? Because I mean, typically if you are doing some, say, some matrix computation or something, then you do something for each row or each column or something like that. You do something in parallel. Again, some intermediate result is computed, and you start on the next thing. So like that. That's how this is proceeding. Okay, but this is actually not a good strategy. Okay, the reason is the following. The reason is that you have put this creation of this thread, okay, inside the loop. Okay, although I just said in the previous slide that threads are lightweight processes and so on. Okay, but they do take I mean, it takes time to maintain them. So setting up a stack for them and all that takes a lot more time than just executing code, the typical addition, multiplication kind of thing, which you would be doing inside inside the regular code. Right? Therefore, what you have is this, in fact, adds to the overhead of this loop. Okay? So you actually don't. Okay? So that's what I've said here. It's quite inefficient since every iteration spawns 5 threads. Okay? And this is costly to create and destroy threads. So here is a different strategy. So first, basically, you create 5 threads, okay, and start them off. That's this thing. Okay. So what do you do here? So your process has some ID, okay, and the run method, inside the run method you put the loop. Okay. So what does the loop do? While not completed, you do one iteration of the ith job. This is the ith process. So you do one job of the ith this thing, and then you synchronize the other threads. So this is like saying you not completed, you do in parallel, and at this point you put a barrier. Okay. Then you, once you have crossed this barrier, then you again do something in parallel and put another barrier. Right. Okay. So what you want to do is, instead of creating and destroying threads, which is expensive, you create the threads only once. Okay. But in the middle of the code you synchronize. Okay. And this is done by putting a barrier. Okay. So then, of course, the next question is, how do you do this barrier? Right. So okay. So again, rather than creating and destroying processes, it is more efficient to create them once and for all and to use a synchronization protocol. Right. So basically, okay, this is if you are familiar with regular expressions, which I hope you are. Then instead of writing a process of the form A parallel B and then A parallel B and then A parallel B, which is what I was doing earlier, what I have written, I have changed this into A followed by barrier, then A followed by barrier, A followed by barrier, and this one becomes B followed by barrier, B followed by barrier, B followed by barrier. Okay, and I have 2 loops of this kind running in parallel. Right. So in this there are these 2 threads, then again 2 threads, then again 2 threads, as you keep on looping. In this there are only 2 threads all through. Right. So here is, of course, the question, which is, how do we implement the barrier? Okay. And some programming languages like X10, for instance, they actually have barrier construct built in. You just need to write something like barrier force, I think it's called. You write out there, and automatically a barrier synchronization is done. But that only raises the question, which is, how does the language itself implement the barrier? Right. So that's the question which we want to address. Okay. Have some ideas on this before we look at the solution. How will you actually do a synchronization? So here are some threads running. Okay. And what you want to do, and here is the where they should go ahead, but what you want to make sure is that there is one point there's one point in between. They've all reached this point, and only after that the next iteration is allowed to begin. How can we program this? it's not very difficult. So this just
wait for the all threads to complete it.
yeah, but now we are actually programming. So you are inside the code of the thread, and now you have to write some code which will say that I have completed, right? So how will I do that?
Can we associate the return value with the run function?
No, the run function is not over. That was the earlier model in which I had a run function, which was over, and then you again restarted. But that we said is inefficient, right? So we don't want to do that. We want to do this in some other way. Okay. So you have to use some means of actually communicating between these processes, right? So what can we do? Supposing we have a shared variable, let's say, that's the most common thing one can imagine. These are all threads running on in the same system. Okay, so the memory is at least shared. So you can imagine that there is a shared variable, or as many shared variables as you want. What will you do with this? I mean, what is the thing which we need to check here? We need to check that these things have all reached this particular piece somewhere inside the code, right? So how can we implement that? You can assume the shared variable is bits or integers or anything you want.
So every time one process finishes, it will go to that shared variable. It will have an allocated, pre-allocated slot. It will change the bit in that slot, and then it will keep checking the other slots to see if those have been completed or not. So it will execute a busy wait till all the other slots have been filled up, and when they're filled up, it will proceed.
Yeah, sure. That's one way of doing it. Okay. So I mean, the first thing which I have tried to do here is actually even simpler. Okay, there is a shared integer count. Okay, and you just count whether you have reached the count has reached a number of processes, right? So in this case 5. So each process just increments count, right? So this is the code inside each process. Okay, when it reaches the end of that section, it increments count and then waits until count is 5. Okay, so that's all you need to do. So once count has reached 5, you know that all the processes have done this. All the processes have reached that appropriate location. Okay, but now there is one problem. What is that problem? The problem is that you have to do this a repeated number of times. So now what will you do? So it means that you have to reset count to 0, right? Who will reset count to 0? Right? So you decide, let's say that one process will reset. So that's one way. Okay. So this is the problem. Okay. You try to reset count to 0. Okay. But maybe one process is very fast and it's just gone ahead and done the rest of its bit of code and already incremented count to 6. Okay, so then the fact that process has already finished its second iteration, okay, is lost. You set count to 0, now it will be incremented to 4 and it will never reach 5. Right? So you have to handle this a little carefully. is more or less what you said, right? So we distribute count into an array. Okay. So these are all instead of incrementing count, you just turn a bit on. Okay. And the test which you want to do is now the following: you add up all the bits and see if they are equal to 5. Okay. Once they are equal to 5, okay, then you want to proceed. Okay. But there is a problem with this. The problem is with this is that everybody is trying to read everybody else's bits. Okay. So which is inefficient. Okay. So how do we solve this? So this will happen, for instance, I mean, if n is something like 1,000,000, okay, then you will see this actually. That this, I mean, the processes will not proceed because everybody is trying to read some billion bits and from somewhere. So the solution which I suggested is the following: that basically there is a coordinator process. Okay. So what do you do here? So in your this thing, you first have some code to whatever you are supposed to do inside one iteration. Then you set your arrive bit. Okay. Then you wait for a continue bit. Okay. So this continue bit will be set by the coordinator. Okay. And when you get this, then you set the continue bit to 0 and proceed. Okay. Now you do your next iteration. Now you keep on doing this in a cycle. And what is the coordinator? Coordinator is very simple. It basically waits for arrive I equals 1 from everybody. Okay. The moment arrive I, it finds arrive I equals 1, it sets it to 0 again. And when it's got from everybody, it just sets everybody's continuous bits to 1. Is clear? Okay. So you still have, so now if n is 1,000,000, you still have this one process which is trying to read 1,000,000 bits, but that's better than 1,000,000 processes trying to read 1,000,000 processes bits. Right? So and of course, I mean, if this n is very large, then you will do more smart things, meaning that once this, I mean, you'll store this n in some data structure, and once the bit is set to 1, then you won't again look for it. I mean, this is a kind of again inefficient because it keeps on doing this loop even after it knows that that bit has been set to 0, right? So you won't do that. Right? So actually, no, I'm sorry, what I said is wrong. This actually does not do it that way. This is not. This is waiting for 1,000,000 things one by one. It's not trying to do it in parallel. So it first waits for process 0, then it waits for process 1, then it waits for process 2, etc. Right. So it's actually very efficient in terms of communication, and you are just guaranteed that all of them. Okay. So this solves the problem. Now it seems like this is a hell of a lot of work to actually do the kind of job which we are doing, which is just some simple thing like this. Okay. That's why I mean, in some programming languages, I said they just provide you a statement which does this. So you will say here, I mean, force or something like that. Okay. And you will continue. Okay. And but the implementation of force will be something like this. Okay. So that's ultimately the code generated has to be something like this. Okay. But now there are more questions. Okay. What are the more questions? First question is, do we have to have one coordinator thread? I mean, then, so this is a fault tolerance question. And what if that thread crashes? Okay, so you don't want that kind of thing if you can help it. Second question is, what is this await? Okay, how can you implement the await? And there's nothing like await in Java, right? So in this case, at least there is a simple this thing, which is that you do a busy wait on that variable. So that await will be implemented as just checking that variable again and again inside a loop, right? So await is just a short form for that piece of code. Okay. Again, if you want to avoid a busy wait, then you have to do more work, but for the moment we are satisfied with that. Okay. How do we get rid of centralized coordinator? Okay. Well, this basically means that everybody has to be their own coordinator, right? So what you do is you arrange the processes in some way. Okay. So you think of them as being organized in some ring or tree or some kind of thing, structure. So here is the code for processes arranged in the form of a tree. So you assume the processes from 1 to n are arranged in some form of a tree, and what will the process at the leaf do? They will do what earlier we saw the processes were doing, which is they will just set their arrive bit and wait for the continue bit to be set. Once the continue bit is set, they will set it to 0 and proceed. Okay. What will the processes in the interior nodes do? Okay. In the interior node, the process will wait for an arrive from the left. Okay. Then it will wait for an arrive from the right. When both of them have arrived, it will it will set its own arrive to 1. Okay, and it will then send the continuous to the left child and the right child. Okay, and finally you have the root process, and the root process will just wait for the left and the right bits arrive to come, and then it sets the continuous. Okay. So this is you might say that this is also to some extent centralized, but at least, for instance, if one subtree is unaffected by the crash, then that subtree will continue to work in a normal fashion, right? So you have to have some code to handle that. Okay. So here what is happening is, no, that's not true. Here what is happening is it sets its arrive bit and waits for the continue bit. So if the parent of this one is knocked out, then this one gets knocked out too. So you have to do something to handle that. Okay. But so this process, the process which is whose parent is knocked out is stuck, but the processes below it, okay, they all get their continue bits in time and they are all working. So this process is on top has become the new root process. So this is a slightly better structure. So this illustrates some very simple things about distributed algorithms. Okay. First is that you have to organize synchronization. Then if you have to do lots of synchronization, then you organize the synchronization in some sort of structure. Okay. So you can say you can maybe pass one token around from I to I plus 1. That's another way of doing it. Okay. Or here what you are doing is you are arranging some tree structure and arrange the synchronization in the form of a wave going up and then a wave going down. Okay. So there are different kinds of ways of synchronizing. Okay. And this kind of technique is all what you need to, but these are all very simple things. So once you learn these, it is extremely easy to implement all these in any particular, and they give you dramatic speed ups in terms of performance. So these are all things which just simple programming tricks which you need to know for this. Okay, so what I've said so far is basically it's not so much concurrency that makes parallel programming difficult. Because concurrency, you just have threads, okay, and threads are provided by a programming language. It's not very expensive for the programming language to implement them. Although I said that it's expensive to keep creating and destroying threads, okay, but creating them once and once in a while and destroying them once in a while is not very expensive, right? So lightweight implementations such as threads can be provided easily, okay, but the processes need to coordinate with each other, and which can be by synchronization, or more generally they might have to actually send some information to the other process. That's also possible, okay, and it is this which is hard. It is implementing synchronization communication which is the hard part of parallel programming. Okay, and then you have various strategies like the couple of strategies which I showed earlier. Okay, so here's a problem. Can I turn on this light? So here is a problem to try this out on. So you join some software company or something, and this is what your boss tells you to do, right? So this is the, okay, so you have 10 threads, okay, and you want to find the first, what is that, 100 million, is it? Yeah, first 100 million prime numbers. I don't know why your boss wants this, but let's suppose so. Okay. So the question is, how will you set up this computation? And I assume you all know how to find prime numbers, right? But how will you set up this computation of the first 100 million primes? You have 10 threads, so you can use parallelism, but you don't have 100 million threads. So you have to do some clubbing together of work. So what would be your strategy for solving this problem? Wait. So you are saying there's an array of primes. So there's an array primes of this kind. Okay, I'm not even sure whether you can write an array this big on a typical computer, but supposing you can, right?
Each of I'm expecting each of my process before it reaches the barrier, it generates one prime. I mean, it basically tests some numbers from 10 each of. Suppose there are 10 processes, so I've labeled them 1, 10, 10.
Yeah.
So each of the process is like going to test primes like 10i. In the ith iteration, each of them is going to after reaching ith barrier, they are going to test primes to the form 10i plus id of this process.
Okay. Maybe something like that. Yeah. this is the, I'm not sure whether this is what you said, but this is one strategy which is like this, okay, right, which is you essentially you divide up the input domain, okay, this is the idea, okay, and you set your block size to 10 power 9, okay, and what each thread does is looks for primes between 10 power 9 times I plus 1 to 10 power 9 times I plus 10 power 9, right, that's what it does, something like this, okay. So we assume that this test prime, this actually does all the work, and you know actually how to find out the primes which are between in a particular range. If you just say give me the whatever 70 million and 463,000th prime, it will go ahead and do that. That process will do that. Okay. Okay. But this is inefficient.
Because each of the block has to depend on the result of the first.
Yeah.
So if the first process finished all the block 10 to the power 9, then only can I use that in the second thread.
No. That you recompute. I'm saying if so you're saying the first process finds out 2, 3, 5, 7, 11, etc. right? And this process, the whatever, let's say the next process, it starts with some, I don't know, maybe something like somewhere around 2 million or 2 billion. This billion, sorry. Okay, so something like 2 billion something it's looking for. It's testing whether that thing is a prime or not. Okay, 2 billionth prime. That process actually repeats this computation. It finds the first prime, finds the second prime, and then only when it gets the 2 billionth prime, then it actually prints it. Yes, so it's doing extra work. That's correct, right? But I do not know, and okay, I don't know enough number theory. Maybe you know better than me. Okay, I do not know whether it's possible to find, if I just tell you give me the 500th prime, whether you can do that without finding the 499 ones before. Okay, at least the algorithm I know would just start that erratogenesis sieve. It will just go start knocking out things, and that's the only way I will find out. But maybe there are smarter algorithms. I mean, I don't know that. Okay. Okay, so there are two problems with this. Okay, first is that there are many primes between 1 and 10 power 9. Okay, compared to the number of primes between 9 into 10 power 9 and 10 power 10, there are relatively few primes. Okay, that's so this the distribution of the primes is not uniform. That's the first problem. And second thing is checking if a number is prime is easier when the number is small, but for large numbers it is harder. Okay, so the workload that you are assigning to the processes is not uniform. Correct? So that's what you are pointing out also, that the process later on has to do a lot more work to actually find that prime. Okay, so this is a dynamic load balancing strategy. So what it does is you just have a counter. Okay, so there is one shared counter, and all you do is you increment the counter, and if that's a prime, then you output it. Okay. So does this seem reasonable? So there is only one shared variable, but it is the counter. Okay. So the counter says basically right now I'm checking whether some 499 is a prime or something. Right. So how are you making use of the 10 threads in this? Each of the threads has this code. Right? Because this is a shared counter. Okay. So when you so what this procedure increment will do is it will return, say, something 500, okay, and increment the counter. So now it's your job to look for the 500th prime. So if some other thread when it calls this, it gets 501, then it's that process's job to get the 501st prime, and so on. Right. So each process will ask for the next thing, okay, and it will look for that prime. Okay. So the two problems which we had, which is that the workload was not uniform, okay, and that the number of primes is not uniform, both of them are tackled by this. Okay, because now the process just dynamically pick up the prime width they have to find, prime number width they have to find, okay, and then they look for that prime. Okay. Fine. So this is, of course, I mean, I'm sure you can implement this better. For instance, you know that this is, I mean, every second number is not a prime, right? So instead of just incrementing this, you can do a more sophisticated thing, which will eliminate a few and then give you the next value, which you have to search for a prime, right? So that is the Eratosthenes sieve algorithm, right? The sieve algorithm, what it does is you have crossed out something, so it gives you then the next thing to try, right? So maybe that you can do instead of increment. That procedure which I am calling here increment, instead of incrementing, you can do a more sophisticated thing. Okay, but even if you don't do that, and even if you just blindly just keep checking every number for a prime. Okay, so okay, but the question is, how do we implement the counter? Oh, no, why should there be a queue?
Like suppose the first thread, it takes the first element of the queue. So the front automatically moves to the next. So by the time the next thread comes, it can take whatever element is there in the thread and check if it's
No, but why do you want to do that? No, all we are doing is generating numbers, right? So I don't know what I wrote some code out here, but right. So you just initially it is set to some value. So remember, initially we set it to 1, I think. Okay, and then all you do is you increment that value. This is all that you do. So this is the only shared thing amongst all the threads. Okay. But this should warn you that there is something fishy here. Okay, that if you have managed to do everything to this point, then there is bound to be a synchronization problem here. Okay. Right. So okay, so the question is, how is this implemented? Okay, so when you look at the machine code, then it will be something basically like you load the value into a register, okay, and save this register plus 1 inside the memory location, okay, and you return this value that you have got. Okay, this is how this will actually be in terms of machine instructions. Okay, right, but this is the problem. Okay, what happens if two threads call this increment procedure at about the same time? Okay, then both of them see the this is a thread local variable. Okay, this is a shared variable. Okay, so both threads might simultaneously copy the same value. Okay, return, so let's say 500, return 501. Okay, store this as 501 and then return 500. So both of them are actually looking for the 500th prime. So this is possible. This can happen. So this is of course an extremely well-known problem in distributed computing. Okay, and I mean it's again the synchronization problem. Somewhere you know that there is going to be a synchronization, and you have to always watch out for that point. What is going to happen there? So this is known as race conditions. Okay. So more generally, this is the way you have a system in which there are two threads, okay, which are updating a shared variable n, okay, and this is basically the code, right? This is exactly what was happening in the last code. Okay. So the problem is that at this point you are not actually sure. Okay, under normal circumstances, after these two segments have executed, we would expect the value of n to have been incremented twice. Okay, but this may not happen. Okay, because it might be that these statements are executed in this way, that is, first one thread gets the value, increments. Okay, then next thread gets the value, but this is the old value, okay, increments, and then both save the same value. This is what I showed here. Okay, so the increments performed by the two threads overlap, and the final value of n is only one more than its initial value. Okay, so this kind of inconsistent update is called a race condition, and this is one of the most common problems in handling synchronization. So here is of course a more standard example. Okay, so this is your bank accounts, and you have so let's say there are 100 bank accounts, and there is a transfer function which transfers money from one account to the other. Okay, and it looks like this. So what it does is, if you want to transfer some amount, and if you do not have that much money, then it returns false. Okay, otherwise what it does is it debits the source account and increments the target amount and returns true, right? But now if you go through the same kind of, okay, now here there is also another procedure which is running here concurrently, and this is the bank is trying to compute how much money it has, right? So all this does is it starts with 0 and just adds the value of the whatever is in each account. So that's the balance which is there in the bank. Okay, and now you can have all these problems. Supposing we execute these functions in concurrent threads. So in thread 1 some transfer is going on. Okay. In thread 2 you are auditing the thing. Okay. It need not be this. It could be that in thread 2 also there is a transfer going on with respect to the same account. That will also give rise to this kind of problem. Okay. So again, thread 2 gets access to account 7 and account 8 after thread 1 has debited account 7, but before it is So this is just an interesting exercise for you to kind of work out a schedule by which this will actually happen. Okay. The audit thing will find a total which is greater than by 500 or less than 500. This is just some straightforward. So we come to the standard thing, which is all of these examples are nothing but the problem of mutual exclusion, okay, to critical regions of program. Basically, what you want to say is when you do that increment, nobody else should be allowed to update to touch that account. So the problem that we come to, even though, so we started with doing something with threads and some very general setting, but ultimately we realized that we need to do some synchronization. When you come to, and when you try to do synchronization yourself using your own code, then you hit some synchronization question, and here it's mutual exclusion. So that's the okay. So of course, as I said, this problem was studied by Dijkstra and all these people long ago. So Dijkstra suggested the idea of a secretary who would manage synchronization, just like we had a coordinator to manage the barrier. Okay. So, and this was actually implemented as a programming language construct called a monitor by Per Prince Hansen and Tony Hoare. Okay. And what Java provides is something called synchronized methods, okay, to actually implement this. Right. So Java has basically what you will say here is you will say that this method is synchronized. You just add one keyword out here. Okay. And what the synchronized will mean is that the method will ensure that any call of this method is atomic. No other thread will come and execute this in between. And more precisely, you can specify actually where you want the atomicity. So here it is how it is done. Okay. So basically there are two calls, wait and notify all. Okay. What wait says at okay, so what is done here is a slightly different piece of code. So what you are saying is, if you have less money in your account, then you wait. Why? Because maybe somebody else is transferring money right now into your account, and you will then have the money which you can transfer. So this just goes into a loop. This is not a loop. This is your queue idea. This actually goes into a queue. It's waiting. Then these two lines of code, they are executed automatically. Okay. And when this is over, then you notify, meaning that the other threads which are now waiting for this method, they can now execute. So what you have is so Java provides you control over that part of a method which you want to declare atomic, which you do using this wait and notify all. These are all predefined methods. So you can, so if you don't try to use any wait and notify, the idea is what's this? Okay, I don't know what this is supposed to be. Okay, the way I've done this is while the audit is running, no other process is allowed to execute. that entire for loop while the process is running, everything else is blocked. So that's how I've done this. But you can allow, for instance, checking the current balance. That can be a non-synchronized method, because when you check the current balance, whether it's happened before the 500 or after the 500 doesn't matter very much to the bank. Maybe the 500 rupees will come a little after you check the current balance. So whatever value is read, it doesn't matter. The bank gives you that. Okay. So this is called. Okay, there are different kinds of these wait and notify work in different kinds of ways, and Java's mechanism is called signal and continue. This is only if you know other kinds of things. So now here is a different setting. So now supposing, so this is a classic readers writers problem. So there is a database, and what you want to say is when a person writes, then that write has to be exclusive, but any number of people can read. Reading is not a problem. Okay. Any number of people can read a value. Okay. So that's implemented like this. You have a class called readers writers, and you have something called data. So this is actually the database. Actually, here you will have whatever the database is. But this is just an example, so I'm just using one number as the database. Okay. And okay, so what does the right? So here is the specification. Several reader processes can concurrently read a database, or one writer process can exclusively read. That's the kind of thing you're doing. Okay. So what is the synchronized the start read process? So you break it up into start read and end read. The start read process increments this counter, and the end read decrements the counter. That's all. So you know how many processes are reading. Okay. And suppose the number is 0, okay, then it tells if any other processes are waiting, it does this. It informs the other processes. Okay. So what does the read process do? It starts reading, and maybe it prints out the data, and then it ends reading. And what does the write process do? What the write process does is it waits for this count to be 0, because the number of readers has to be 0 when it's going to write. It waits for this, so it waits and then catches the exception. Okay, and increment does something to the data. So here I've just said increment, but and then notifies everybody else that I have finished my writing. So then readers can begin reading. And this is a more detailed this thing. A reader can be written as extending the class thread. And this is how you set up the whole system. So I'm not going into the details of this. Okay, so there's something still better in Java, well, better or worse depending on what you think. So first, it's not just methods. Okay. Any object can also be synchronized in Java method. Okay, so you can do something like the following. Okay. Here is an object O, okay. And so here somewhere you say you synchronize O, and then you can do wait on this, and then somewhere else in some other thread maybe you are doing synchronize O, and you say O dot notify O. Okay. What this O dot wait says that put me on the queue which should give exclusive access to O. Okay, and this says okay, I'm done with whatever I was going to do. Now you can let anybody else access the object. So it's not just methods which you can synchronize. You can synchronize accesses to any object. do even more. So Java provides a class called locks, and I remember in the first lecture you were telling me about locks. So you have an interface called lock, okay, and there are two methods: lock, which puts the lock on, and then you can enter the critical section, and then unlock, which you do when you exit from the critical section. Right? And the way to use this is something like this. So if you want, so this is some object of the lock class. Okay, you call its lock method. Okay, then you put a try out here, and then you write whatever you want to do in the critical section here. And here you say finally you unlock. So even if there are exceptions or anything, you will always before you the moment you get out of the critical section, even due to an interrupt, you will always unlock. You don't leave the lock on. And in addition, you require the thread to be well formed, which means that each critical section should be associated with a unique lock. If you have two locks for one critical section or something like that, then Java doesn't, it says it's unpredictable what will happen. So it's your job to ensure that everything is associated with a unique lock. So if you look at, say, synchronized methods or synchronized objects, the question is how are they implemented finally in Java? So they are all implemented using locks. So they will all be actually implemented using calls to this lock class. Right. So now, so our earlier shared counter example can be done in the following way. So you have a counter. It's initially set up with a value I. Now all you do is when the increment method, it locks first the this mutex is what you are using for the counter, and what you do is then you read the value. So this is all atomic essentially. These two things are atomic, okay, and then you unlock it and then you return it. So that race condition that we're talking about simply will not happen. So basically race conditions can be created when threads run in parallel using shared memory, and Java provides synchronized methods, synchronized objects, locks, all of these to program exclusive access to shared memory. And internally each synchronized method, object or lock has an internal queue. The predefined wait method suspends the currently executing thread and puts it on the object's queue. Similarly, the lock method will suspend if the lock is already acquired by another thread. Okay. And what notify all or unlock does is it releases the lock and wakes up the suspended thread. Okay. But now we have a question, which is how are these locks implemented? Once we know how to implement locks, then we know how to implement synchronized methods, synchronized objects. So how does Java implement the locks themselves? Somehow it has to provide an okay, so we'll stop with that. Questions?